So the last test for chi-squared is chi-squared test for independence. So there's 3 that you learned in this chapter. The first one was goodness of fit. Again, 1 variable, 1 population. So you should look for, when you're trying to figure out which test it is, 1 row. Or they give you like 1 set of proportions. Homogeneity, which is what we did yesterday, is 1 variable in 2 or more populations. So you should have some sort of matrix. Today we're doing independence. Independence has to do with 2 variables in 1 population. So you're going to have to do another matrix. But it's mostly going to be like a 2 by 2 matrix. Whereas yesterday it was like 2 by 3 or 3 by 2 with something different. The testing procedure basically is identical to what we did yesterday. In fact, 2 years ago on the AP test, the FRQ that was a test was chi-squared for independence, but they accepted homogeneity because it's basically the same. The only thing that's going to be different is really the ho and the ha. So everything else is the same as what we did yesterday. So, and I'll tell you what keyword to look for in terms of which one's which. Your conditions, like I said, are the same. So the first condition should be the observed cell counts are from a random sample. No, because we're testing for independence. So they don't, and we're only looking at 1 population. So the only one you got to put independent random sample is the homogeneity one. The other 2, you're just looking at 1 population, so it's just random. Number 2 is the same. The expected cell counts are greater than or equal to 5, therefore chi-squared distribution may be appropriate. And again, you're probably just going to write it out before you even find the expected cell counts. That's okay. On your quiz, they should be all greater than 5. You can still cheat and do what we did yesterday and combine into other categories if you need to. But on the quiz and the test, it should be okay. So this is a chi-squared test for independence. We're basically trying to prove, the key word you're looking for independence is when you see the word association. You're trying to look for, is there an association between the 2 variables? Are they independent of each other? Are they dependent of each other? And then condition 4, it's not on here, but it's kind of the same as yesterday. You do P sub RC, the true proportion of whatever, like of each gender and the proportion who have a tattoo, something like that. Your ho and your ha. This one's like the easiest ones to remember. The null hypothesis is that they're independent. The alternate is that they're not independent. So the null hypothesis is that the 2 variables are independent. Make sure you state it with context. Like I'm just giving you a general form. So you would say like gender and having a tattoo are independent. The alternate is that they're not. The 2 variables are not independent. Again, stated with context. So people can a lot of people flip these around. That's the mistake they make. They'll flip them around. Here's what I always think. Remember, we're assuming that this is true, that they have no association. We're trying to prove an association. So we're trying to prove that they're not independent. So that's how you can remember which one's which. The reason, I don't know why we don't say dependent. It's kind of like that guilty, not that innocent, not guilty thing. We just either say they're independent or not. You have to make a table of expected values just like yesterday. We'll do it in the calculator. Your test statistic does not change. Again, here's the expected cell count formula. You don't necessarily need to memorize this. It may show up on the test as a multiple choice question. Degrees of freedom are just like yesterday. Rows minus 1 times columns minus 1. So, the only thing that's weird about the conclusion, we either reject or fail to reject. So, if we reject the null hypothesis, we can say there's an association. If we fail to reject, you would say there is not an association. Okay, so yesterday we were looking for, are things the same? Today we're looking at, are they connected? Questions? And then we just have one example. Because by this time you're pretty much experts at write-ups. We only have one more in chapter 13. So, our example for the day, Salem High School seniors, is there an association between gender and having a driver's license? So suppose that a random sample of 100 Salem students, seniors, were taken and subjects were asked their gender and whether or not they had a driver's license. Does the data suggest an association? So whenever you see the word association, think independence. If I was asking, is it the same for male and female, then that would be homogeneity. This is not goodness of fit because you have two separate variables, license and gender. Okay. So, for our conditions, it was a random sample. So observed cell counts from a random sample. Now, again, we're going to assume all the expected cell counts are greater than 5. And then we'll do the expected in a minute. All expected cell counts greater than or equal to 5. Therefore, chi-squared distribution may be appropriate. So this is chi-squared test for independence. So condition 4, the proportion of each row and column. Again, you just need to give me like both variables kind of in context. The true proportion of each gender having a driver's license. So can you understand what you're looking at? So for our testing, the null hypothesis, again, your two variables are gender, having a license. So are they independent, not independent? Gender and having a driver's license are independent. Your alternate, thank you, gender and having a driver's license are not independent. Okay, so now we're going to make our table of expected values. And again, just like yesterday, you don't necessarily have to include the total. I squished that in there. So we're going to do this the same way we did homogeneity. You're going to put the observed in matrix A, do the test. Matrix B will spit out the expected. So if I go to matrix A and edit 2 by 2 matrix. Okay, again, do not include the totals. So you put in your observed. Then I go through and I do my actual test. So I got to go down. I want to do the chi-squared test. Not the goodness of fit one, just the regular one. Test C. Observed, expected goes into B, and then you can hit calculate. So we're going to write out our test statistic at some point, but give yourself some room. And then you can write a chi-squared of 3.011 gives us a p-value of 0.0827 with 1 degree of freedom. Now in this one, again, you can find your expected values either by going to matrix B and looking at the edit section, or I think there's enough. Usually a 2 by 2 is okay. I can read the numbers. So here's your expected values. And again, for your test statistic, I just need to see the first and the last in terms of the formula. Do you understand what the formula is? Bless you. So 36 minus 31.96 squared. If you want to write all 4 out, you can. Like on the quiz, you might have time, but on the test you might have time. This test isn't as bad. So our chi-squared was 3.011. Did I go too fast? Questions? Okay, so it's just like yesterday. If you want to list the degrees of freedom here as 1, alpha is 0.05. As long as you just make sure you got to put degrees of freedom somewhere. I like to put it in my sentence. So, is our p-value greater than or less than our alpha? Greater than. So we're going to fail to reject that they're independent. So it looks like there's no association between gender and having a license. Since our p-value is greater than our alpha, we have evidence to fail to reject, bless you, the claim that gender and having a license are independent. So since we're failing to reject that they're independent, it means that they are independent, so there's no association. It appears there is no association between gender and having a license. Okay, question.